So good afternoon, good morning, good evening, whatever time of day you're happening to watch this. I hope y'all are having a great day. And you should have just finished watching a little video that did not have any voiceover. It was only music and notes. And it talked about Galileo. It gave you some additional information about him. So we're going to continue with our discussion about Galileo today and about his historic experiment that he performed having to do with cannonballs and gravity. So let's get started. So in the video, it showed Galileo as a student sitting in a chapel and watching chandeliers swaying back and forth as a result of gravity. And it also mentioned that he is the father of modern science. So when they say the father of modern science, what they're talking about is he was one of the first people to perform and record the results of experiments forming the basis of the scientific method. So the other question I was going to ask you is if you realize that any weight that is suspended in air is going to respond to gravity in some way or another. It may not respond a great deal, but if it's suspended on a single cord or this is a pendulum in this picture off to the side. It's called a Foucault pendulum, but if anything is suspended like that in a straight line on the end of a chain or at the end of a cord, it's going to end up responding to gravity one way or another. And in this particular pendulum, once you start it, and notice that the tip of it is sitting where it can touch that mountain of sand. Every once in a while, this is in a museum. They have them in museums all over the world, actually. But you every once in a while will see technicians go in and stop the pendulum and scrape the sand off so it's smooth it out so there are no tracks on it. And then they'll start the pendulum again. And this pendulum will swing back and forth for a little while, but then you'll notice that the pendulum starts moving in a circle, kind of a circular fashion, and that's because of the rotation of the Earth. And in fact, if you've ever seen a grandfather clock, the grandfather clock has a pendulum that swings back and forth and back and forth, and it makes the sound of the tick, tick, tick as it's going. If you'll notice, if you look up inside of a grandfather clock, that pendulum hangs within a track. So that narrow track that's there keeps the pendulum swinging in a straight line. And if you didn't have that track there, the pendulum would actually start to sway back and forth, just like the pendulum here does. So that might be something you want to try when you get out. If you're just curious one day and think about this again, you might want to, see if you can make a pendulum respond to the Earth's gravity, because it is kind of fun to watch that happen. All right, so what Galileo did was he was interested in discovering whether it was true, because at that point in time in history, the thinking had been formed way back thousands of years ago that the Earth had a certain force. I don't know that they even called it gravity, but that gravity was dependent upon the size of the object. So an object that was lighter had less gravity, and an object that was heavier had more gravity. And he was trying to find out if that was actually true after watching these pendulums, or these chandeliers rather, swinging back and forth. He realized that regardless of how big the chandelier was, if the lengths of the chains were the same holding the chandeliers, they tended to sway back and forth at the same rate. And so he obtained permission, because this was already an engineering disaster, the Leaning Tower of Pisa. He obtained permission to go up into the tower and drop cannonballs. Not throw them, not chunk them, but just drop them to see how they would behave in free fall. So the assumption was the more that they weighed, the heavier they were, the faster they would fall. But Galileo was kind of puzzled by this, and that was the reason he wanted to do this experiment, was to see if they really did fall at the same rate, or was it dependent upon their mass, their actual weight. So time after time, with repeated sizes, various sizes and repeated experiments, he found that they always hit the ground at the same time. So what did he prove, and why was it important that he continued to test his hypothesis? So wait, what was his hypothesis? So at this point, I want you to take the piece of paper that you have, and we're going to complete this activity together with the exception of the last section. So stop right now. Make sure that your name, both your first and your last name, is on the paper. and then make sure I can read it. And I'm going to need to be able to read everything that you write. And we're going to take our time to fill this out accurately. And all that you are required to do at this point is to copy information. All right, so you need to copy it neatly. The only thing that you will have that I expect you to do anything creative is on the very last section where you make a diagram. So let's go ahead and get started with the first section. So the first section, first of all, let's talk about how people thought this was going to turn out. So if you notice there on the Leaning Tower of Pisa, you've got the heavier cannonball under the old idea of falling faster than the lighter cannonball. And this is what people assumed would happen. All of the scientists, people who were investigating things at that time, probably weren't really investigating anything. They were just repeating what had been said to them over the decades, over the centuries, over the millennia. And so Galileo was really pretty forward thinking. Okay, so let's look at the first thing. The first thing you need to fill in is the title. Notice that it is filled in here for you. It says Galileo's Historic Free Fall Experiment Using Cannonballs. So I'm going to wait a few seconds and let you get this filled in. If I had the Jeopardy music to play in the background, I would play it, but I don't. So the title should say Galileo's Historic Free Fall Experiment Using Cannonballs. So if you've already finished copying that, start thinking about what the hypothesis was that he was testing. Because at the time, remember, they believed that gravity pulled differently on different things. And he was thinking about the idea that gravity was a constant. In other words, it was something that didn't vary. All right? So here, next line, here's the hypothesis. Gravity is a constant force that causes all objects, regardless of their size, to fall at the same rate. This was the hypothesis that he was working on. So a hypothesis needs to state either what you're planning to test, or sometimes we have a hypothesis that's called a null hypothesis, which means if this was a null hypothesis, he would expect the cannonballs to fall at different rates because that's what the thinking was at that time. So null means no change, right? But he was proposing a change. So the hypothesis should say, gravity is a constant force that causes all objects, regardless of size, to fall at the same rate. So I'll give you a couple of seconds to finish that up. All right, the next section is the independent variable. Now remember that you have two kinds of variables. There are lots of different factors, but there are two kinds of variables. And the variables in this case, what was he manipulating? What was he changing as he dropped these cannonballs? He was changing the weights. Okay, so the independent variable was the weights of the cannonballs that were dropped. Some of them were really massive. They were big, large cannonballs. Others were smaller. They actually had cannons of different sizes back then to deliver payloads, if you want to think about it like that, but cannonballs that were of different sizes to do different amounts of damage on things. You know, you needed really small cannonballs maybe to knock down a wooden fence or a gate or something, but a larger maybe stone wall or a ship or something like that, you would want to launch a really big cannonball to do maximum damage. So the independent variable here was the weights of the cannonballs that were dropped. So remember that the theory at the time was that if a cannonball was really large, it would fall faster. If a cannonball was really small, it would fall more slowly. So the dependent variable, in other words, what were the results? The dependent variable looks like this. It was the time it took for any cannonball to reach the ground. All right, so they thought that the more massive ones would reach the ground faster because that depended on their weight. They thought the smaller ones would reach the ground more slowly Again, that was dependent upon their weight. However, so if you have dependent variable there, let's look at what the results, how we want to phrase the results. We know that the cannonballs hit the ground at the same time. So what you want to say in your results is, regardless of the size of the cannonballs, they all fell at the same rate and hit the ground at the same time. And then a follow-up statement that says this proves that Galileo's hypothesis was correct. So once I'm going to give you a couple of minutes to finish copying all of this and make sure that you've got it correct, and then we'll talk about the diagram. All right, so as for your diagram, whoops, I need to sit up a little taller. Here we go. As for your diagram, here are a couple of ideas about what you could draw. You could draw something kind of silly like the one on the left, which shows Galileo, you know, with a little tiny cannonball and a great big cannonball, obviously on a leaning tower. The one on the right shows, you know, the cannonballs falling. One of them is a little bit smaller than the other. The one on the left looks like it might be a little smaller than the other. You could draw something not even this technical. You could just draw, you know, a leaning tower and two objects falling, one larger than the other. You could show them hitting the ground at the same time. You could show them way up in the air as they've just been released. Whatever you want to do is fine. But you do need to have some kind of a diagram. If you remember the one that was at the beginning that showed how they would fall at different rates, and then the one that showed next to it was how they actually fell, you could do something like that as well. But there does need to be a diagram on there. I need you to try your best to demonstrate your understanding of what this was about by giving me a diagram on there. Hopefully there are no questions, and we'll get this done very quickly. Tomorrow you're going to be reading another article. This one, I believe, let's see, yesterday should have been something about bats, right? And the one tomorrow is about climate change and how it affects poorer countries, particularly populations in Africa who are struggling right now. So if you have any questions about this, you can always turn the paper over on the back and put your name or put your question on the back. If you'd like to send me a question about something you'd like to have answered, that would be great. I'd be happy to entertain that as well. So hopefully you'll have a good rest of your day and that this made sense to you. Take care, and I look forward to hearing from you and seeing your drawings. Take care. Bye-bye.